and point D first. Okay. So we're going to draw our free body diagram. Okay. So based on our free body diagram, we have a by over here. And we have our dy. And then we have our point A over here. And we have our point C somewhere over here. This is our point B. And this is our point D. And over here, we have an equivalent load. So this equivalent load is 50 times 10 to the power 3, okay, 0.8 plus by 2.4. So this will be equal to 0.8 plus by 2.4 times by 50 power 3 is equal to 160,000. Once you got the position, immediately put in the distance. Okay, this is good advice. So the distance from here to here is equal to 2.4. Okay, so I'll write down the formula in case you guys forget. Plus by 0.8 divided by 2. Okay, so 2.4 plus by 0.8 divided by 2, 1.6. Okay, so get all your distance sorted out. So from here to here, this distance is 0.8. And then we know from here to here, right, that distance is 2.4 plus 0.8 is 3.2. Okay. So from here, we know our values. We are going to apply a static analysis. So we can say that we're going to take our moment. And we're going to take our moment at point D. Okay, so this means that anything that's anti-clockwise is positive. Anything that's clockwise. So By is going to induce a clockwise direction. So this is equal to minus 3.2 By. And then the equivalent load plus is going to generate anti-clockwise, okay, from point D. Excuse me. 160 times 10 to the power 3. And I forgot another distance. Okay, I forgot this distance from here to here. So that distance is 0.8 plus 0.8 plus 2.4 minus 1.6, 2.4. So this is 2.4. So from here, multiplied by 2.4. Everything is equal to 0. So By is equal to 160 times 10 to the power 3 multiplied by 2.4 divided by 3.2. So 160 power 3 times by 2.4 divided by 3.2 is equal to 120 positive. Positive means your answer is correct, or the direction is correct. Okay, so it's pointing upwards. So from here, the next thing we will do is positive is going up. Dimension of forces in the y direction is equal to 0. Okay, so you have By 120 minus by the equivalent load, which is 160, plus by dy, the whole thing is equal to 0. From here, we found that our dy is equal to 40 times 10 to the power 3 Newton. Okay, so you have these two values. Okay. So once you have these two values, then you can start constructing your shear force and bending moment diagram. Okay, so I'm going to again take this figure. This should be like a quick revision for your regarding shear force and bending moment diagram. Okay. I don't think it's difficult. It's just maybe you forget. Okay. Right. So let me try to put this to scale perspective. So we can start by sketching the shear force and bending moment diagram. But I want to also help you recall, okay, how to form the equation, because some of you might not have the experience to guess the profile of the shear force and bending moment diagram, but you can mathematically do this, okay? So I'm going to teach you how to derive the shear force and bending moment equation. Okay, and yeah, as I said, it's not. So the first one we're going to do is between point A to point B. Okay, so i.e. the limits of this function is 0x to 0.8 meters. Okay, so if I were to sketch this, this is our point A. Okay, and over here, this is your geometric datum lengthwise. So this distance is your x. So you have a load coming down here. So this will be 50 times 10 to the power 3x. Okay. And then we have a distance from here to here, which is x over 2. Let me write better. So the distance from here to here is x over 2. Okay. So we are going to assume positive shear, positive bending moment. Okay. So when the analysis is left to right, okay, positive shear is coming down, positive bending moment is going anti-clockwise. Later on, I'll show you an example when we do right to left, you just have to flip the direction. Okay. Okay. So from here, we are going to do static analysis. Summation of forces in the y direction is equal to 0. So if you look at the diagram, or the free body diagram, we know it's minus v. Sorry, not this is not vx. Okay, so this is v as a function of x, and then you have m as a function of x. Okay, so minus v as a function of x minus by 50 times 10 to the power 3x, the whole thing equal to 0. So v as a function of x is equal to 50 times 10 or minus 50 times 10 to the power 3x. Okay, so this is your shear force diagram equation, okay, between 0 to 0.8 meters. Okay, so what does this mean physically? Okay, what does this mean physically? So if we were to, I go to, okay, so I'm going to put in some magnitude. So you have shear force. Then we have V, and this is times 10 to the power 3. You have 80 you have 60, you have 40, 20, 0, and then we have minus 20. I'm going to stop at minus 40. Okay. And then we have our x-axis, right? So what you can see, so this is our x, and then if I were to draw the vertical line coming down, and then I draw another vertical line. So you can relate where we are on the beam. So we know that the x-axis is 0.8. Over here is 3.2, and over here is 4.0. Okay. So by looking at the function, right, is a linear function, and the slope is negative, right? So the next thing we ask ourselves at 0.8, right? What is the value? Okay, at 0.8. So based on this equation, and so this equation is 0.8, so slightly less than 0.8, right? So if you can put 0.7999, whatever. Okay. So minus 50 power of 3, okay, times by 0.8, you get minus 40. So the first value over here, right, comes over here. And because the function has a negative, your gradient is negative. Okay. So this is your first diagram. Okay. So over here, this is equal to minus 40 times 10 to the power of 3. Okay. So that's your first point. Okay. So then the next point, right, comes to now is at point B. Okay. So at point B. So at point B, x is equal to 0.8. Now at point B, we have to be careful. Why? Because we have a by. We are aware that we have a by, coming up here. And we calculated our by earlier. Our by is equal to 120 times 10 to the power 3. And then, oops, I forgot something. And then we have something over here, dy, and dy is our 40 times 10 to the power 3. Yeah. I don't want to do bx equal to 0.8, because the next thing I want to do is I'll do the shear force diagram, bending moment first. Okay, so bending moment, summation of moment z at point x is equal to what? Is equal to 0 over here. So what I'm doing now is I'm going to take moment at the, I'll change color, sorry. I'm going to take moment at the red dot. Okay, we're going to take moment at the red dot. So we have mx, m as a function of x is going anti-clockwise positive, okay, and then 50. So the 50 is also going in the anti-clockwise relative to the red dot. So it's equal to plus 50 times 10 to the power 3, okay, x multiplied by what? X over 2, the whole thing is equal to 0. So m as a function of x is equal to minus 25 times 10 to the power 3 x squared. Okay. So that is your function for your bending moment. Now you can already now see the relationship between shear force and bending moment diagram. Okay, so I can also do this. So m of x is also equal, you integrate 0 to x Vx dx. So when you integrate 0x, okay, so you have minus 50 times 10 to the power 3x